Hi, my name's Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome to Ultra Hydrogen, this 19th of May 2024. How is everyone? Can you hear me? Sorry for the delay. I was looking for my microphone, which I'd forgotten to bring, so I'm back on my old microphone. So hi, Craig. Analog Driver Bob Boob Lazar, that's a new one. John Weir, Artifact EBB, Corky Goss is in the house. Nick Moore. Hi, Ken Pratt. Hi, Nick Knock. Hi, Gordon Doherty and Mr. Gate Mode, Overwound Games. Hi, Humberto Diaz, Estonias, Samuel Keeley, indeed. Vanilla Isis, Yin Gazda is in the house also. Hi, Joss S, Daniel Stott, Benjamin Rives, Sonny Mod, and Earthworm Jim. How are we today? Well, I'm going to start off. I'm just going to clip a piece of video out of another video. But this was sent to me by Simeon Hein. So thank you, Simeon Hein. So if you just give me a second, I'm going to clip this out of this video. And we will be ready to go. So yes, you can see I've got my old microphone here, which is actually a better quality microphone in terms of the richness of the audio. However, it's not so convenient because it gets in front of my screen when I'm using it. So yeah, there we go. So give me a second with this, and I will be with you. Okay, so we're going to go there, and we're going to go here somewhere. Okay, hopefully this will work. So thank you for your patience. I'm, how should we put this? Pretty jet lagged, I have to say. I feel like I'm in the middle of the Atlantic somewhere. So if I fall asleep on you, I'm very sorry. I actually feel like I'm on a boat, but there we go. Okay, so this video was of a hurricane, and as I have said to you quite recently, one might argue that, and I'm talking to myself over here, I need to kill some other browsers, otherwise things are going to go a bit south. Okay, let's hope that doesn't cause a problem there. Okay. Right. I think that I might have decoded the rotor Sata square, and I suggested that it meant that the divine creator from alpha to omega repeatedly comprehends and works with whirlwinds, where you can remove the from alpha to omega repeatedly if you wish, because that's the less certain part of it. But regardless, what I want to share with you is this clip, and actually the original video is here, so for those that want to look it up when it's finished the adverts. It's called Nebraska and Iowa Tornado Outbreak, 26th of the 4th, 2024. So it looks a bit like this. There we go, and we're going to look at a very small segment of it. I will give all the links as usual to anything that I mention in my blog at remoteview.icu. So I'm going to put this up in here. If we can do this. Mm-hmm. Is it going to work? Oh no. Don't die on me. Oh no. Epic fail. I'm not having a very good day today. It's frozen on me. Okay. All right, we'll go to the original. If that'll let me do that. Will it let me do that? No, it's not letting me do that. Okay, let me do this. Okay, I'm going to go into Premiere because it'll let me do it in there. This isn't what you were expecting, was it? So Tammy says, Bob, what days specifically are you interacting with attendees at Cosmic Summit? As Sunday is Father's Day and Monday is Classroom Day, it's a trek to attend the wrong or at least optimal day. So for those that are interested, I will be speaking on Saturday, I believe in the morning. I will clarify that on my blog in the coming days for 1 hour. I will be available at all times, and I'm required to be available at all times, from the Friday evening disco all the way through to the end of Monday. So I will be on call, let's say, for all of these various events. And I'll be at dinners and so forth. So I guess the classroom day on the Monday is where, you'll be able to specifically ask me questions. And I think personally, from my point of view, I will go through subjects that the audience wish to hear. I do know quite a few people are already coming, so that's great. So thank you for that. Oh, thank you, Craig. That's very kind of you. So I'm going to just create a dummy video here, and I'm going to view. Okay, let me see if this works. I didn't like that either. I'm having no luck here. Okay. No, it's not liking anything. All right, well, this is awkward, but I will go to the actual video. It's just unfortunate I can't. Yeah, Monday would be the best day for one-day attendance, yes. You can get a streaming pass, and obviously that would allow you to see what I say on the Saturday. But if you want to come and, I guess, interact with me, then probably coming on the Monday would be the best bet for that. And it's quite reasonable. And I think actually today I shared a discount code for that. Maybe I didn't, but maybe I did. Can't remember. Like I say, I'm in the mid-Atlantic somewhere. Okay, I'm going to go back to the original YouTube here, if I can. Let me see if I can do that. I am having issues today. Oh dear. Is there a live streaming for Monday? I don't know. I don't know if there is actually. Yeah, I don't know if there is. I'll check with George. If George is in the chat lurking, then please maybe he can say. Right. Let's do it this way. All right, this has been probably the worst start ever. George Howard, he's the organizer of the conference. In case you thought it was another George that I might know. Okay. This isn't how I wanted to present this, but it is how we're going to have to look at it. I'm very sorry to the people that had to suffer this in tragedy in terms of the event here. I can't imagine what it would be like, but obviously you can get some scale here from the perspective on these power lines. I imagine they're power lines, not telegraph poles, but regardless, you have one here, one here, one here. There's can't really see anything over here. Maybe there's another one in here, another one here, and then you can see one here. So if we know the height of this one, which is in the near frame, and we know the height of this one, which is behind the object in question, then we can size the object. We can also see the width of the road here and the width of the road in the foreground. And again, that gives us perspective cues for those people that want to precisely work this out. Now, in this video, actually, thank you very much for taking the video, but it's incredibly risky to be this close to a tornado, as I'm sure people are aware, and also perhaps maybe one should school oneself on not saying certain things when you're watching an ongoing tragedy. But yeah, so whoever's barn this was, or whoever's roof this was, they refer to this as a roof. Okay, this is a roof section, and I don't believe it to be on fire. There is no flames. There is no indication of flames. And we've seen this a number of times where roof parts fume incredibly, such that in this case, you've actually got the daylight such that it is behind this, and it's completely obscuring the daylight here. Totally and utterly obscuring the daylight. So if I step through this, and on YouTube, you can do that by hitting the dot button on your keyboard, which might also be represented as a right arrow. You can see that they are zooming into this as they are watching this object. And this is a sheet, I think, again, of gypsum, or what you call the plasterboard. And it takes a bit of time. Now, interestingly, in the vector, and you can start to see this turning. It's turning around here. Okay? It's turning around here. And in the vector, it's pointing down to this telegraph pole. So it's pointing down to this telegraph pole. And as it moves like this, we suddenly have an electrical event. Actually, there's a telegraph pole there. This might be on the actual wires. Very bright event. Now, these two streaks here, in my view, are typical of a lens flare type effect caused by the camera. This is something that you see all of the time in certain type of cameras, and so I wouldn't get too excited about that. But you can see that the intense bright glow from that is reflecting off this material here, and it's still not penetrating very far into it. So it's obscuring the light of the sky behind, and it's also not allowing the intense light from here to penetrate too far. But as you can see this rotating round, rotating round, rotating round, rotating round. Out of it, here, you can suddenly see this more solid object here. And it's still fuming furiously. Absolutely furiously here. Fuming in free air, right? I don't believe it's burning. And then it kind of does, they move around, and you can see even at this angle it's fuming, even though it's kind of lost its direct connection to the vortex. It's still fuming, it's still fuming. And it starts to come round the larger vortex rather than that smaller sort of finger of God, as I call them. Still fuming. We'll play this real time in a minute so you can get an idea of what this is like. Fuming away, fuming away. So you can see kind of this roof section here, but the fuming appears to be coming from underneath. And soon we see that it actually looks like plasterboard. Here we go. Same kind of thing. There you go. There's your plasterboard. Now, I wish I could zoom into this. If I had it in Premiere, I could. Here's your plasterboard sections. Okay? And it's gone on major fumage. Yeah, major fumage. And when it comes over to the right here, this is what Simeon Hein noticed. So thank you, Simeon, when you are watching this, if you're not watching it live. It just goes out of shot and they pick it up again in a second. And like I say, I'll come back and play it real time. So over here to the right, you'll see it picked up here. Yeah. It's still fuming. It's fuming on its way down here. Again, it's gone into full-on fume. I don't think this is on fire. Now what happens is it gets to this point here and it just suddenly stops fuming. There's a glitch in the encoding there. It just stops fuming. It literally stops fuming. And then it touches down to the ground. There we go. La-da-da. Right, so I'm going to go back and play that real time from the beginning of that section. So you can see it's to 11 seconds there, and where is it? So 48 seconds there. It's really not that long a sequence. 20-something seconds. So it comes into it. There's a little cut before, not this. So here we go. I'll just step that back to the beginning, and we'll watch this real time. Okay. Plasterboard, plasterboard. That is some poor person's roof. Fuming, fuming. Stop fuming. Absolutely crazy. And I think that you're going to find lots of these kind of things turning up in videos. And we're going to have a huge data set. Now, there's two experiments I would like to do if I was here. And I don't want to be there, but if I was. One would be, after that's touched down, you know, after that has touched down over here, I would like some samples of that thing, right? Okay? If I had my microscope with me, I would like to go and look at some of the material right there. The other thing I'd like to do, and this sounds absolutely bizarre, is if I knew where a tornado was about to strike, I'd like to put down a selection of materials. So some plasterboard, some metal, some of different types, like brass and aluminium and steel, mild steel, stainless steel, wood, and see how the tornado would affect the different materials. In an ideal world, if there was no risk involved. I'm not suggesting anyone does this. Sheets of carbon, yes, vanilla isis, all kinds of different things. But so I want to thank the Storm Chasing channel here and for this video, Nebraska and Iowa tornado break on the 26th of April, less than 1 month ago. I am sorry for the people that suffered this indignity. I hope that you have found some way to get through this difficult time. But this is science in action. But what is going on is the question. And why does it fume furiously when it is clearly in this part of the finger of God, you know, which is so intense, the beam coming down from this, it's doing electrical things in its point of focus. There we go. Absolutely bonkers level of fuming. All right. And then it comes over here. And it kind of falls out. You can see it's fallen out the effect. And when it's fallen out of the effect, it literally stops doing it. JDP said, I should watch Terrence Howard on Joe Rogan. Yes. Here's the thing. I've seen 3 long videos from Terrence Howard. He is clearly a very erudite and articulate man. He shows all of the skills of a well-trained actor for remembering facts and whole sequences of text. You know, I'd love a conversation with him. I would. He has an interesting mathematical anomaly, which he trades off, and that's okay. And it's a real one. He also has some claimed patents, both historically and forward-looking. Now, one can get patents, especially if one's got money. It doesn't mean they will work. And there are many ideas that people have that they have all at the same time. And so, you know, there we go. Back in 2000, 2001, I did a development for a site called Staying Close with another group. And it was where people could upload their photos and what they were doing during the day to any one of their friends and family. I'm glad I didn't get involved with that. I'm glad the .com crash happened. You know, there's a lot of things whose time... The idea has come. The time for that idea has come. There was a lot of truism said in that 3 or 4 hours or whatever it was. There was a lot of truisms. There was a lot of references to names we all know. I didn't get anything from it that I could act upon. And honestly, when I'm looking at people's material, I'm looking for the thing, the one thing, the 2 things, the 3 things, the 4 things, the whole group of things where there is something you can act upon. So maybe I missed it, but it was interesting, and it was quite a nice dynamic. Okay, so I like the fact that people like that are getting a chance to have their ideas aired. That is very, very important. Because he's clearly a thinking man. And that is... It's really good. And he's not necessarily on, you know, the defined path. But, you know, I wouldn't argue that all of science is wrong because I found one anomaly in maths, which is a provable factual anomaly. So, you know, he was using a medium which has been designed through the application of existing accepted maths. That is the internet and the communication technologies and electricity and all those kind of things, you know, enabled that communication to happen. So it can't all be wrong. So, but it was interesting nonetheless. Okay. All right. So what are we actually meant to be doing here today? I had all kinds of things planned, but I didn't do them. I planted seeds in the garden, so it's going to be raw. So if you recall, we did an experiment. I'd wanted to do this experiment probably for 2.5 years or something since I first heard Shishkin mention that he, Kurols, and Dubovik, sadly departed Dubovik, has determined rather that hydrogen was 2,000 to 4,000 times easier to produce etheric matter from than any other element from lithium and beyond. And of course, Tesla used according to this wonderful book here by Jerry Vassilatos, he preferred and found that beryllium, magnesium, and aluminium were the only elements that he found suitable to make clean etheric matter streams. And of course, they're all heavier than lithium. So if you can do it with hydrogen, then one might expect it to be easier. I guess when you go beyond aluminium, you're going to get fragments of ions and electrons onto the etheric matter that make it dirty, potentially with the right disruptive discharge or the right energetic process. You could expel just an electron and a proton, nucleus of protium, from hydrogen and get the etheric matter out, and almost immediately that electron and proton will reform into a hydrogen atom. So the etheric matter, the magnetotoroelectrical radiation, this, according to them, potentially a cluster of background neutrino equivalents, this is neutral, and so it will come out. But because it's not carrying all of the rest of the baggage from fragments of an atom, and the atom can easily reform, then you get a clean etheric matter stream from that. So I kind of thought, well, obviously you've got hydrogen in water, and if we can get hydrogen out of that water, then that is available in situ for the low energy nuclear reaction to take place in this whirlwind, in the tornadoes or the fractal tornadoes that are produced by this sacred geometry, magnetohydrodynamic structure that forms when you have a node in a standing wave in sound acting upon the metal. Now, they say that you only need 5 electron volts to do this in terms of the impact, and one could argue this would happen in a range of different metals. The same similar effects seem to happen in copper, and so yes, you might have the impact being able to split the water to produce the hydrogen and to fully charge separate the hydrogen. However, it dawned on me that I had seen some research a long time ago where aluminium was used to produce hydrogen in the field. And I actually shared one of the first papers on that on the blog, and it's called Reaction of Aluminium and with Water to Produce Hydrogen. And here it is. And it's a study of issues related to the use of aluminium for onboard vehicular hydrogen storage. US Department of Energy. This was from 2010. And the people conducting this were John Petrovitz, a very sort of Slavic name there, from Los Alamos National Laboratory, and George Thomas, not a Slavic name, from Sandia National Laboratories, both retired, okay? And the purpose of this white paper is to describe and evaluate the potential of aluminium-water reactions for production of hydrogen for onboard hydrogen-powered vehicle applications, blah, blah, blah. There is a requirement, but the reaction here is, and you can see it, 2 aluminium atoms plus 6 water molecules goes to 2 aluminium hydroxides plus 3 hydrogen. Okay? So 2 aluminium atoms yields 3 hydrogen atoms and a hydroxide, which would be alkaline. So if you recall, what we did was we ran the experiment to see if it produced hydrogen. It would appear to have produced hydrogen. Now, we had a question. Was that really hydrogen, or because we could see it was getting a little bit steamy in there, could it be that more water vapor was being pulled into the Cirrus 2 quadrupole mass spectrometer, and that was being split and ionized, and some hydrogen was being produced by that in the Cirrus mass spectrometer, And because there was more water going in, we then saw more hydrogen. Well, that's when Alan Goldwater, my dear colleague, had the genius idea to see if what was leaking out of the not great seal at the bottom of the setup was actually a combustible gas. And it turned out it was. So that was very satisfying. In hindsight, I might have liked to have put a little slit and caught the hydrogen into a test tube and done the whoop test where you light it with a taper. That would have been really satisfying. However, I didn't do that, and that can be for another day or another person. So, although this reaction is thermodynamically favourable, it does not proceed due to presence of coherent and adherent layer of aluminium oxide that forms on the surface of aluminium particles, which prevents water from coming into direct contact with aluminium metal. And, this, it's quite obvious because, army pans, and you might have had an aluminium pan back in the day, they don't just fall apart when you start boiling water in them. You literally have aluminium pans which you cook in. So, and it's because of the passivation layer. It's highly reactive, and it gets covered in a coating of aluminium oxide that protects it. In fact, a lot of frying pans have actually got this hexagonal tubes of aluminium oxide, which then get filled with PTFE or whatever to produce non-stick pans. Okay. The key to inducing and maintaining the reaction of aluminium with water near room temperature is the continual removal and or disruption of this coherent, adherent aluminium oxide layer. And so my hypothesis was, in my head, and then I saw this, is that the sound could do that because it was smashing this stuff off. And therefore, rather than relying on just the mechanical the mechanical production of split water and full charge separation from the cavitation process, I was thinking in my head, I was imagining right at the point that you absolutely need atomic hydrogen, it was synthesizing it with gusto because there was a chemical reaction that was assisting the process. And so you had the bare aluminium, oxygen, and hydrogen all in play in that environment. And that, for me, maybe in my mind, said, well, perhaps this is why aluminium is so good at this process. I've done 90-second experiments, and you get the yin-yang, and on the center of the vortices, you start to get these apparent transmutations going on. Okay. A number of reaction-promoting approaches have been investigated for the aluminium-water reaction. These include additions of hydroxide promoters such as, now bear this in mind, sodium hydroxide, oxide promoters such as aluminium oxide. Hold on a minute. Okay, all right. Aluminium oxide is actually already on the aluminium. Okay, so if we smash the aluminium oxide off the aluminium, it could be that accentuates the process. So it goes slowly and then all at once. But what happens, and it says, and here, salt promoters such as NaCl. So what happens if we actually have reactions, nuclear reactions, that produce, the physical reaction, smashing that aluminium oxide off, is going to produce this oxide promoters here, Al2O3. And if we have a nuclear reaction that synthesizes either sodium or sodium chloride, we're going to get a hydroxide promoter or a salt promoter in this reaction. Very, very interesting. Okay? So you can go through this paper. They talk about the money and how you would need to make it. All of the aluminium-based approaches propose methods to circumvent the protective layer of aluminium oxide, thus allowing the reaction with water to proceed. The hydrogen produced via such aluminium-rich water reactions might be employed to power fuel cell devices for portable applications such as emergency generators or laptop computers. There is also a suggestion that aluminium water reactions might be used for hydrogen storage on fuel cell powered vehicles. The purpose of this white paper is to describe and evaluate the potential of aluminium water reactions for production of hydrogen, primarily aimed at onboard hydrogen powered vehicle applications. Okay, all right, so here's your basic reactions. They have 3 different chemical products that come out. So 2 aluminium plus 6 H2O gives you 3H2, 3H2, 3H2. But depending on the amount of H2O involved, you can end up with some 2 aluminium, and it has a different name down here. So the AlOH3 is gibbsite. The AlOOH is boehmite. And the other one is aluminium oxide. So there is actually one reaction that produces aluminium oxide. And we've already seen up here that that will start. Where is it down here? Somewhere here. This is an oxide promoters that may actually promote the process. Okay, so it's not only smashing off the aluminium oxide, but sometimes it's actually making aluminium oxide. And in that case, it's kind of a self-reinforcing process. Okay. The first reaction forms aluminium hydroxide, blah, 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 blah. All are also highly exothermic, right? So when you saw it was effectively at 100 degrees and it had been boiling at the end of that experiment, then some of that, possibly all of that heat could have been coming from this reaction. But I have to say, it was not a lot of aluminium. It really was not a lot of aluminium. Why would it be boiling? Well, we also put 35 watts of sound in there, and it was reasonably well insulated. And the reality is that if you put a billionth of a watt in a very insulated water-filled container, sooner or later it will boil. So, this experiment was not about, are we producing excess energy? Okay? Nuclear or whatever. It was mostly about, just from sound and distilled water, could we produce hydrogen? And if so, in my mind, that means the hydrogen is most likely to be produced exactly at the point that it is needed, so it lives long enough to participate in the reaction, because H2 is not paramagnetic, but H minus and H, as in a proton, they both have a magnetic moment and can go into the magnetohydrodynamic structure and take part in these reactions as per my hypothesis. Okay. So they've got the thermodynamics here of what happens. So all of these reactions are thermodynamically favorable at room temperature past the melting point of aluminium, 660 degrees C. All are also highly exothermic. From room temperature to 280 degrees C, this is the most favorable and stable product, rather. From 280 to 480 degrees C, it's this one, and then above 480 degrees C, aluminium oxide is the most stable product. Right, so it's not saying that these aren't produced at different temperatures. It's just saying that once they are produced, the most stable is these compounds, respectively, at the various temperatures. Okay. Okay, so you can go through it, but basically they look at the various promoters. This is the experiment, and then they have some various graphs and show, pure system aluminium only, mixed system, okay, and they actually show here the pH, okay, hydrogen production versus pH for aluminium oxide powder mixtures. Okay. Hydrogen produced in 1 hour reaction. Okay, so quite a lot more hydrogen. Obviously, as it gets more alkaline, you get a lot more hydrogen production. So as we start to produce hydrogen, we are producing a more alkaline environment, and so it starts to accelerate. So that's not surprising that we had a lot more hydrogen produced, and it rapidly took over. Okay. All right, so HDU generation time. Okay, so anyway, basically they're adding sodium hydroxide, sodium chloride, or aluminium oxide to it, and that is that. Okay, so that's our first paper. And so I'm going to show you a couple of videos. I'm going to hopefully get the audio coming through for you. And then we will go and have a look at the analysis. Now, what I'm actually going to do for you today is this is why I lost nearly one night's sleep this week. I was absolutely determined to find out how to install the Cirrus Logic recall software so that you, like me, could review the mass spectrometry data at your leisure. And I finally found on some GitHub where someone had listed the install code, which is very simple, and I'll show you later. And I have the software running, and it's a very old piece of software because it's around about 2008 or something, and I have it running on Windows 11 on Parallels for Mac desktop, and it runs really well. So you can run this on basically any PC you have around the house or know of, and then you could review the data. And then I'm going to talk about some element isotopes that the mass lines could indicate, and also molecular lines, and I'll show you how to go through those. And then I'm going to ask you as the crowd to go out, and I'll give some hints and tips, and this is where you can come in and do something and see what you think these mass numbers are referring to, and I'll give you my view, but I'd like to see what you think they're referring to. And I think over the next week or so, we'll be able to nail down the whole process of what's going on. Okay. Alrighty. And I don't want that one. I want, where is it? Okay. Okay. All right. Let me just check I've got this right. Is that the first one?
So here.
Wait. Not that one.
So here we are.
Oh, sorry. Give me a second. All right. So this is the first one I want you to look at. Actually, this is the first one. Oh, dear. Not a good day. Okay. One. No, two. One. Okay. All right, 3. Okay.
So I took some of the sediment from the bottom of the ultra gas production synthesis experiment, and I placed it on some of the source or starting material for the experiment, the aluminium foil, and I drove off the water using a little bit of heat from underneath, and we can look at these samples here and see what we can find.
Okay, I'm just going to rewind that just a bit there. So basically, I started off, I pipetted out the bulk of the water here, and then I used a spoon, which was probably cleaned, to extract some of the detritus that had collected at the bottom. I then put that on some of the source aluminium foil here, and over a mild flame I let it dehydrate it. Okay, now the interesting thing is you can see this scum here. Okay, now is this a deposit of aluminium hydroxide, I don't know. Something like that, possibly. Anyway, this is the material that we had there. And then the second video I want to show you is this one.
This is a sample of the starting material for the aluminium ultrasonic experiment.
So I prepared a segment of the starting material, and on here you can't really see it because of the carbon tape. There is actually a chunk which I will show you in this video.
So here we are looking at the slightly drained tank of the ultra experiment and the detritus at the bottom here. And I have this small ferrite magnet here in a bag, and I'm going to see if we can pick up any particles from the bottom of this tank for analysis on SEM. Oh, it's picked up one particle there. That is definitely a candidate there.
Okay, so that particle, I just got one because I had this fairly weak ferrite magnet and I couldn't find any neodymiums, so I had to park that idea. But we got this one particle, and that is alongside, over to the side of looking at the raw material here. Okay, so it's somewhere here. You can't see it because it's black on black. Okay, so let's have a look at that analysis that we have there. Okay, and here we go. It's called raw foil and sediment, and this will obviously all be shared. So this is our chunk here, and I will show you what it looks like there. And I have to say, this looks remarkably like the chunks that I got out of Suhas Ralkar's 200-hour plus 4.5 kilowatt of sound at 19.2 kilohertz sonicated fuel for his echo reactors. You see this interesting little kind of disc down here. These kind of flat plates or fragments, but it's an agglomeration of all kinds of things smashed up and put into this blob. Okay, there seems to be a kind of a layer here. So this is something that I've seen something similar before from Suhas Ralkar, and so let's have a look at what that actually is. I did a couple of sample points and an area point here. Okay, so we have an area on 414. Okay, we have a point on 413, a point on 412, and a point on this area here. So what I'm looking at here when I'm choosing this, I want an average over a large area. Here I want something that's the mid-gray. I want something that's the very white section, and something that's the general body of the material here. Okay, so here you can see carbon, calcium, iron, aluminium, silicon, magnesium, sodium, iron. Sorry, I said iron already. Now, they're very clear peaks. They're very clear peaks. However, they're not very large numbers. This particular piece here is, can't remember why that's only showing 68.8. It might be still doing the sampling there. But it had some titanium in that area. So titanium is fused CO2. Look at the amount of carbon in here. Huge amounts of carbon. Okay? 84.95%, and that is in what? 413. 413 over here. And 60% in 411. 411 is that averaged area. So when we are looking at this here, it's saying that a large proportion of this material is carbon. And that is what we see spewing out of these things. Okay, carbon. Okay. So this is a magnetic particle. So Why is it magnetic? Well, it's got iron in there. And this particular piece, although it's not got the right sum there, that was about 10%. It could be that there was a reasonable lump of iron or a number of chunks of iron in this, sufficient that that was able to pull this up. Now, could the iron have come from the steel in the base? Possibly. But it does appear that this process does produce iron, as we've said before. The other thing is I couldn't really identify what this peak was, and this was this spot point that I did here, 413. And so I did a close-up on that bright spot there. So I went and did a close-up on this bright spot. And there's a couple of bright spots together, 3 little bits here and another one over here. And what it came out as is bismuth. Bismuth at 22.17%. So I don't know what's going on there. There was also a bit of copper in there. Could this have been contamination from something? I don't know. But it's bismuth. Okay? I don't think... I can't imagine that this came from this, because this is the... It's not actually a stable element. It's actually technically unstable. So I suspect that this is a contamination. Although it seems to be fused into this blob, and the blob is largely what you might expect to come out of this system, I still am reserved in sharing this. And it seems to have a little bit of copper in there as well. So I don't know. I'm not so convinced that this is bismuth. Rather, it is bismuth, but I'm not so sure that it's bismuth coming from transmutation. But maybe. What else do we have? Right, well, what did the raw aluminium show? Well, the raw aluminium in this case showed essentially aluminium, an incredibly small amount of oxygen, and interestingly, a small percentage of iron. And the iron are these little, the flecks that contain a small percentage of iron. So here, 2.42% by atomic atoms, okay, are these slightly lighter flecks. Okay, other than that, it is aluminium. So this, for me, indicates that and I actually did buy some 5/9 aluminium foil, but it never arrived. I bought 5 sheets and they weren't cheap, but they never arrived, or they got lost in the post or whatever, I don't know. I wanted to do that. I wanted to do that experiment with the 5/9 aluminium. I bought 10 of them, I think, 10 by 10 centimeter sheets, and this experiment was meant to be run with that. I had to fall back on standard aluminium kitchen foil. Now the question is, where does this little iron come from? Maybe it comes from wherever the aluminium source is. Maybe the aluminium source is partially scrap metal. Who knows? But there is a small amount of iron in here. So if you look at the light flakes, we're looking at about 2.42%. Okay? But what we're not seeing here is all of these other elements that we saw up here. We're not seeing the magnesium, the silicon, the calcium, the titanium, the sodium. Is this fluorine? I don't know. Maybe. Fluorine. And these ridiculously high levels of carbon. I mean, like, the mean across all of those, including the sample area. And the sample area, actually, as I said before, is this large area here. So it would appear that when you're not actually selecting a particular thing that's a lighter grey or a white, when you're selecting the bulk of it, it's basically highly rich in carbon. Okay? Highly rich in carbon. Yeah. Okay. What else have we got in this? I don't know whatever else we got. So thank you to Magic Sound Lab, Alan Goldwater, for supply of this SEM. Right. Now we get to see these little aluminium clips. Look at these little beauties. What are we looking at here? So that's our bismuth. That's our raw aluminium. That's a close-up of the raw aluminium. What is going on here? What is this? This, my friends, is one of the torn off pieces of aluminium. But look at it. It looks very much different to what we have witnessed in the past. Firstly, it seems to be smoothly covered with something. that has these fracture lines here. And then it has these blobs, these kind of round blobs. And then these little cylinder type structures. Okay? These little cylinder type structures, which almost invariably are thin on one end, are fat in the middle, and thin on the back end. What is going on with that? Thin, and they seem to have a ridge in the middle. What's that? They're all fairly consistent. And then what's going on? We have these pads of something. It does look like Australia. I did think that, Martin Kemp. Yes, it does look like Australia. What is going on with this? We have these darker pads, and out of these darker pads, we have literally it's like this is a floral sponge, and then all these things are stuck into it. What is going on? What is going on? And these things tend to be at the edge. Now, I could show you, both from my own experiments and from those of third parties, where you get these fuzzy grey blobs that seem to go around the edges, chewing away at the material. Are we seeing the death of those things here? Are we seeing like the extreme when they've been consuming for an hour or two? Is that what we're looking at here? I don't know. There is a huge blue ocean of opportunity to find out things here. Okay, so looking in a bit closer, look at this. It's like a pad which has a certain thickness, and then it's growing out of it. This is like a little dome. Oh, hold on a minute. It's a little bit torus-like, isn't it? But look at this. Here, look, this almost looks hexagon-like. It's got a straight edge and then a curve. A straight edge and a curve. Isn't it amazing that nature produces lots of straight lines in a world that can only have atoms that are spherical? Here we go. So look at this growth out of here. And this is what I mean. These things. You see this little one here? It has a straight bit, and then it has a little kind of ring around it, and then a cone bit. A straight bit, a ring around it, and a cone. Straight bit, ring around it, and a cone. What is going on? Straight bit, ring around it, cone. I mean, what? Eh? All right, so what are these things? Well, I'll do a map on this. Here's our map. I'm going to put it over there so you can see it without me being in your way. And it would appear that this base area here, it's actually distorted in this. It should be more like that. Okay. Yeah. Clearly, this is aluminium. Okay? These rods with these rings around them. This is aluminium. Okay? It's also oxygen. So these things are aluminium oxide or something like that. But why this shape? Why these cylinders with a like a pencil end on one end and a cylinder and a ring around it? What could that be about? The other thing is this straight edge and this straight edge are rich in carbon. Okay? So these pads here would appear to be rich in carbon. This pad here, rich in carbon. Okay, is this the carbon that then ends up in that big blob? I don't know. You're going to have all of this data to mull over. Right, so now I'm going in and I'm looking at this thing a little bit closer. I'm looking right on these blobs here, 421 and 420. What do we see? What is going on here? Look at these peaks. They're very clear. We've got a potassium peak. We've got a sodium peak. We've got a chlorine peak. We've got a sulfur peak. We've got a phosphorus peak and a silicon peak. Of course, we've got the aluminium. Of course, we've got the oxygen. And yes, we've got the carbon. Now, these, whilst being very clear peaks, they're not actually very large numbers. They're very small, in fact. This is atomic concentration. So the potassium's reasonably high. And the chlorine's reasonably high. And the sodium's reasonably high. Magnesium, not so much. Phosphorus and sulfur, not so much. But the X-rays, the characteristic X-rays are quite clear. Now, what do we learn from that US Department of Energy paper? We learned that, yes, aluminium Al2O3 oxide, aluminium oxide can be a promoter of this process. Also, what can be a promoter of this process is sodium hydroxide and sodium chloride. Well, here we go. We've got sodium and sodium chloride. And of course, you could argue that if the logic follows, potassium would do the same thing. Yeah? You could argue that I think we saw some magnesium there. That could be a promoter as well. In the same way that sodium would be. Magnesium hydroxide or sodium hydroxide, these would both be promoters. So not only have we got the cavitation ripping off the aluminium oxide that can be a promoter, we've potentially got transmutation being a promoter. Okay? Let's see. Okay, look at this again. Another look here. Magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Okay. Very, very clear peaks. Very clear peaks. Look at that chlorine peak. Look at that potassium peak. Look at that sodium peak. Very clear peaks on this. Again, another sample point here. This is 423. So that I've actually got the sample points separated. Very, very clear peaks. Okay. From distilled water. Processed in here. Now, is there anything that could actually do this? Well, if we look at our reaction tables on nanosoft.co.nz and we put in the reaction starting products, let's say we've got H2O, and aluminium. Those, let's say, are because you've got aluminium oxide on the outside. These are the only things you've got. You've got species of hydrogen, one species of aluminium, and species of oxygen, right? What do we get from that kind of reaction here? Well, what are we seeing here? Let's say, do we get any sodium out of these from a potential linear reaction? So I'm going to do a find here, and I'm going to go Na. What have we got? We got any Na in there? No, we don't see any Na. Really? No? Have I spelt that wrong? I don't see any Na. Maybe I do need the neutrinos. Okay, so if you have neutrinos, you get Na here. What is producing this Na? It is, in this case, oxygen 17 and oxygen 18. In this case, it is oxygen 18 and oxygen 18. And they are our two cases in that reaction. So where is the Na coming from? Is it a secondary product? I don't know. What about chlorine? Don't see chlorine there. What about magnesium? Plenty of magnesium. Magnesium all over the place, right? What else have we got? Some silicon. Lots and lots and lots of silicon. One of the main products here. Okay. What else? Phosphorus. Lots and lots of phosphorus. We saw calcium earlier. What have we got? Calcium. Lots and lots of calcium coming out. Okay, so in just a first exchange reaction, we can end up with a lot of these kind of products. Let's go and look at see what we get when we do fusion. So go to fusion reactions. We'll type in the same query like this, and we'll execute that query. So under fusion, what do we get? Fluorine there. We got fluorine. When we got hydrogen and oxygen 18, we can fuse through to that. We got sulfurs, we got the iron, we got calcium, sulfur, chlorine, look at that, and sulfur at the top there, okay, with these products in play. We know that when the matter collapses, it produces carbon. So if we go back and we add carbon in there, what does that give us? Like I say, I'm just showing you how to do these things. I'm not saying this is the answer. My point here is to start to really show you how you work out what may be going on. Okay, so if we add carbon in there, does that change anything? Does it change our situation on sodium? We still got the reaction here. We still got the reaction here. And that might actually be showing 100. Yeah, I think it's a limit. I'm limiting to 100 here. That's my problem. Maybe it is really 100. Okay, so there's other reaction. Carbon-12 and carbon-12 can end up with a proton and sodium-23. Yeah, so carbon-13, carbon-13, carbon-13. Yeah, so there's other reactions that produce sodium when you are working with carbon in play as well. Okay, so anyway, these are the things that are observed. Are they contamination? Maybe. I don't know. But whatever is going on, when you get these sodium and magnesium and potassium in there and chlorine in there, this process is going to accelerate. Okay, so I've done another couple of area samples on here. This one 422 and this one 423. I'm looking mostly at the top. This 423, I'm looking a little around the side. And again, obviously aluminium is the big peak, but there are very clear signals on sodium. And I don't think that magnesium is there in that shot. Chlorine, sulfur, phosphorus, silicon, and potassium. Okay. Okay, so that's that one. So I think the key takeaway from this really is that in the original material, I don't see any fluffy carbon biscuits with hundreds of thousands stuck on top. Okay? I don't see these little biscuits with the hundreds of thousands stuck on top. Okay? In the other piece of, I don't also see this level of carbon going on. Just not there. Okay. But, my friends, that wasn't all we found in this, because what I then did was I looked at the actual foil, and I only had chance to look at one piece of the very top foil before I ran out of time. The foils are still there at Allen's. Next time that I'm able to go to California, I will take a good dive through those. They're in a sealed bag, and so they should be just as I left them. So I'm just going to get this up here. If you give me a second. And it's not in there. It is in here. I think. No, it's not that. Not that. Okay, so I'm just going to show you these. I'm going to quickly run. I will publish these. This is the analysis. So you can see the little fragments of foil on there. So this is looking close. You can see these areas eaten out with these oxide structures being produced. This is the actual layer of how the oxide looks. This is the aluminium oxide. And I look at this, so you can see. So this is, I'm looking at the whole top aluminium spot here. Okay. So you can see these regular clusters around the place. Let me go back here. Look, there's a circular area here with the hundreds and thousands on top. Another one on the edge. This one here, and another two on the edge. They're typically on the edge here. And then there's fragments left all over the place. So these are all the little fragments we had. You can see the holes where it's punched a hole through here, 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 here. Whole collection of them there. Like I say, I'll publish this. Rather nice little hole there. Now, we've already shown that these things have a range of elements in them. Okay? A range of elements mostly around aluminium with the relevant interaction of the other elements available there. You can see how highly concentrated it is around the vortex hole. This one here, I'll actually show you the Word file. I'm saving you a couple of hours here. Hardcore people go and look at it. This one around this hole, which looks very damaged, this has actually got chromium, manganese, and iron in. I think probably these could come from the steel. This could come from the stainless steel. Yeah, it's just interesting that they are around the hole in this instance. So I'm trying to save you a lot of time here. This particular blob here, again, you've got some chrome and iron in here. Now, okay, from here, you're starting to see ones that really do look like they are vortical structures in nature. So you've got a hole right in the center, and you've got something that's fairly geometric going around here. I'm just going to play this through, actually. You see, you've got a pentagon type structure here, and then the material arranged around the outside. Okay? And does it look like there's an inflow here, inflow here, inflow, 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 inflow? Maybe. Inflow, 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 inflow. That's for you, Steve. Look at that. Lovely, lovely thing there. Really, you can really see the pentagon there. Here, very much a donut. So, when you're looking at this, this is starting to get close to being a 20 micron. My friends, I think that if you ran an ultra experiment for long enough using copper foil, I believe you might end up seeing something similar to what we saw in Bin Chuan Huang's DHX2 reactor. I think that what we're seeing here after the time that we ran that reactor is the same kind of structures forming. I think we can replicate fairly easily using simple equipment what we observed in Bin Chuan Huang's system. Now here's our money shot, but we'll go and have a look at this in a few minutes. But this is on part of the reactor, and it is a near perfect torus, and it has, drum roll, a hexagonal boundary to it. A hexagonal boundary to it. Bearing in mind, I only got a chance to look at part of one part of this experiment. Thank you very much, Benefice Science TV. Great. That's really great. So he says, I've been out of commission for a few weeks, but new videos are coming soon that you will enjoy. Wonderful. Likewise, I will share all of this. Now, what I like about this is in the background you can see, because this is the top sheet. Let me go and find you the image of the top sheet that as I was putting it in here. Let me get that for you because it is relevant right now. Okay. So what I did was this is the very top sheet. So what I wanted to start with was a undamaged area. And I thought because it's on the top, then some things might have settled onto it. Right? So this is the top of the top. Okay? I didn't want to look at any of these damaged areas at this time. So this is the section there sitting under on the SEM rather. Okay, and here you can see the two pieces side by side. So that is the actual sheet, and here it is on top of the sample holder in Alan Goldwater's SEM. So I took a section out, and that is what we are looking at in these images from the video of the analysis. Right, let's queue up the right bit. So I suspect that we would find a good number of these structures similarly placed elsewhere. Now, interestingly, it has two dark spots down here. And this central spot here. Two dark spots and a central spot. And look at it as it builds this up. It is a thing of great beauty. I'm going to speed through this. So there we go. We have these two highly enriched carbon spots down the bottom. And this hexagonal boundary with this beautiful contrast against the aluminium in the background. Beautiful contrast with the aluminium in the background. And this is literally like an incredible impact crater. It has this little nipple in the middle. So it has the ring, but also a crater, but the crater's got a raised bit in the center as well. And then it has this substructure around the outside. So I'm gonna go and look at this in a little bit more detail in the Word file. Give me a second. And then what we're going to do is we're going to compare the elements that we found with the gases that may have been produced and what those gases might be comprised of. I actually did a line scan on this as well, and it seems to think that in the center here there is some fluorine. It's not a lot. It's very little, in fact. Okay? So I'm not convinced of that. It almost looks like it's down in the noise. But what you can see is that within this structure here, The magnesium is not a lot, and then it comes up. Okay? This is the magnesium here. Magnesium is coming up, and then going down, and then coming up in the central spot, and then coming down, and then coming up on the ridge. So there's a central spot, and you're going to see this in a minute on some of the other elements here. But it looks like magnesium is being synthesized, and magnesium is a product that we saw potentially being synthesized in the calculations we did earlier. So when we go here, and I'll take out the carbon, so we just go, I'm going to just keep it to, so you can see it. I'm going to zoom in. Just going to take out the carbon. Okay. We'll run that query again. Execute query. So, magnesium. Well, I'll just search for it here. Magnesium. Okay. Aluminium plus aluminium goes to magnesium plus silicon. Aluminium plus aluminium goes to magnesium plus silicon. Aluminium plus aluminium goes to neon 20 plus sulfur 34. So on. So if you've got any reaction, in my view, that occurs in here, that if it's both the same starting products like aluminium and aluminium, then it's the one that's the most energetic, in my view, that will take place most likely. So the first one that occurs is this one, reaction 166729. Aluminium 27 plus aluminium 27 goes to magnesium 24 plus silicon 30. Plus silicon 30. Now look, we've got argon gas in here, we've got neon gas, we've got other gases that might occur in here. You might get silane gas or something. Okay? All right, so the magnesium here is clearly going up on this edge. It then goes down, and then it goes up in the center, and it goes down, and it goes up again. Thank you very much, above all things. That's very, very kind of you. Okay? So is this the impact of a cavitation bubble? Or is something else going on? Because you're actually making a lighter element, aren't you? Well, you're making a lighter and a heavier element if you go by this equation here. Okay? But anyway, definitely here. And basically in the noise on the outside. Okay? All right. Now, if we go back to... where was I? Yes, that's our line. And I go through the line and I build a document here. So again, look what we've got here. I'm currently looking at the edge here. This is sample 440. Yeah? And look what we have in 440. We have magnesium and silicon. Magnesium and silicon. What did we show was synthesized in this process? When you take 227 aluminiums, you get magnesium and silicon. Magnesium and silicon. I think this is pretty conclusive in my view. We've got the whole hexagon stuff. We've got the breakdown products just like Matsumoto observed. These kind of patches. But we have, other than oxygen, which we know is in there. We know oxygen is in there because we've got water. We know aluminium is in there. And we know we started with a little bit of iron, right? But the foreign products that are in this spot, and a higher concentration in the center and on the edges, is magnesium and silicon. Magnesium and silicon. I think that this is a potential evidence of a reaction going on here, which has energy, and what does it have? 3.97 million electron volts. To put that in context, if you are splitting hydrogen into two atomic hydrogen, I think that's like 4 electron volts or something. It's not a lot. It's the most you can get in a chemical reaction, but it's not a lot. This is like 1 million times more. So the energy yielded from this one reaction here potentially could cause the splitting of 1 million atoms of hydrogen. And I think to chemically split water, you need, I don't know, to make OH separate, you need like 2.3 or something, 2.36 or something electron volts. So whatever, it's going to be 1 million times more energy than is needed to do those reactions from one interaction here. And this would indicate to me that potentially this is occurring in these cavitation systems. It's a totally beautiful little structure here, and I can't wait to get back on that SEM and find more of them. Let me show you what it looks like. Here I've got some other images here. Look at that. Isn't that a thing of beauty? Look. And these two things down here are carbon. They just like a carbon. Let me see if I can get the right one here. Okay, so look at the contrast here. This is the aluminium, right? Very centered, this structure. The ring, the central spot. See what it looks like on the carbon. Two very, very strong spots here with our center spot here. Have we got a vortex and an anti-vortex, and this is the disruption zone? I don't know. I actually don't know in this case. That is the oxygen. Look how... I mean, you know what this is? This is because this is built up. This is built up, and so is this bit in the center. This is a ring spot. Ring spot. Okay? This overall structure is built up. Okay? Carbon, that's the SEM. That's the widescreen SEM. But look how this is not just aluminium here. This is, I would argue, a lot of carbon. A lot of carbon is deposited on there, which is most of the breakdown product. And then around the central spot here, we have the magnesium and silicon, which is minor products there. Okay. And there, all of these images will be shared for your viewing pleasure. Okay. This is some of those aluminium oxide sections. These are aluminium oxide layer. And then these are some of the emerging pads of material. Okay. That's the mixture. But here, this for me is a very important money shot. We have aluminium splitting. 2 aluminium splitting to magnesium and silicon, and that for me is captured in the video that I just shared with you. This one with the line scan. Okay. All right, so what I'm going to do now is I am going to actually I'll where's the documents? Let's have a look. Top aluminium. Let me get this open in Word. Okay. Did I put the line scan in here? I don't know whether I did. Oh, there we go. There's the line scan. So yeah. Look at the magnesium there. Your magnesium and silicon coincident on the ridges. Coincident on the ridges, and then that central bump right across there. That for me is pretty conclusive that something, I mean, is it just an impact? Don't know. But whatever's gone on in that cavitation has been sufficient. It would appear to, for every 2 aluminium atoms that interact, you can do a million chemical reactions. So for each of the atoms detected, each of the pair of atoms detected, synthesized here, you can do a million chemical reactions with the energy that's yielded. Okay? All right, so I'm going to pause for now, and I'm going to load up my PC version on Parallels, and I'm going to show you the data on the application and how to lay that out. And then I'm going to show you how you can determine what element isotopes there are. I'm going to share that PDF with you, and then I'm also going to share the approach to finding molecules that could account for what is observed. Okay, so with that, I'm just going to put up the hold frame, and I'll be with you in a little while. So give me a sec. I'll go and visit the little boy's room. Was I talking to myself? Okay. It's just not my day. Okay. All right. So I think you can hear me now. Can you hear me now? Can you hear me now? Yeah. Okay. All right. So what I'm about to show you is a technique that will be applicable next week when I also share the raw data from the active test of a thunderstorm generator that was built by Phil Dubois in Santa Cruz. And I will share a lot of video associated with those tests and the raw data. So you will be able to see for yourself the ability of the thunderstorm generator to, it would appear, clean up and increase the quality of the burn of the gases that might be coming out of that, and also how that may be occurring. And so we'll take you through what you see. Thank you, Vanilla Ice. It's very kind of you. And so, you know, I think it's going to be very interesting. It was a very satisfying couple of days. We learned a lot, but the skills I'm just about to show you now will tool you up for being able to read that data with a good degree of understanding of what you're seeing and what you are not seeing. Okay, so without further ado, I will try and set this up so I can show you what I want to show you now. Okay, so I need to get my PC going over here. If I can remember how to do it. So I'm going to share you a piece of software. It's called MKS Mass Spectrometer. I have the actual CD capture, but it was very disappointing, and I tried to find... Actually, I used GPT-4o, and I asked it to create from the text exports that I'd done at Allen's, because I couldn't get... I spent, nearly a whole night trying to find a way to get the DLLs or whatever working so that you guys would be able to see the raw data. And I was banging my head against a wall, and we just needed this particular install code to be able to get it working. So when you're going through the MSI on the PC, it got to a point where it said, please type in the special install code to install this software, and nowhere did we have that install code. And so I thought, no. Okay, so then I tried to create some Python scripting, and this is why I'm a bit exhausted this week, so that you would have a piece of Python script that you could run in an IDE that was online, and so that you could create scalable vector graphics from the text that I had exported out of these data sets. But I thought, this is just taking... Surely somewhere someone had got this. Anyway, I managed to do a search and come up with this archive here that's referring to this software. And they just listed a whole bunch of these install codes. And one of them is EasyView. And I tried it and it just worked. And it's actually the name of the software. So it's just hilarious. There's the CD setup code, and he says, I think it's just EasyView, and it worked. So there we go. You'll be able to run this if you have a PC or if you have Parallels on your Mac. What you're going to see is the recall software, which is another subset of that software which will allow you to look at this data from the ULTRA experiments and also from the thunderstorm generator, both control and active runs. And I think you're going to enjoy being able to have access to this data. And I think, you know, there's some immediate things you can get out of it, but there are other things that will come out in the wash. And so this is another piece of homework for you to look at the ratios of things both before and after in both of these experiments. Okay. All right, so that's that. That's easy view. Okay. So what I've got here is, and it's unfortunately set up for a 4K monitor. So I've got to readjust it and everything, but it'll probably work okay. These are two parts of the experiment here. It's Ultra 6. And maybe I can bring up the other window here. Is the other window? Ultra 6 trend. Yes. Okay. So what we're looking at here is the whole experiment. And we'll set this up here. So we've got the setting the mass spectrometer. I'm going to put this down here. Okay. So the whole experiment ran for about 6 hours and 30 minutes. And the spectrometer took about, how is it? About 2 hours, 45 minutes or something to get to a stable state. If I move my mugshot around about here. And then I have these notes in here. That's when the Ultra experiment was added. Sorry, it's a little bit small, but it just is the way, okay? And so nothing really massive changes here. I think we had to take it off because of something. And this spike here, this is in OH. I don't know. It might have been something to do with that. Anyway, over here is where we first turned the sonication on. So the sonication started at 3:25 and 55 minutes. Okay. And then we had 1, 2, possibly 3, 4, 5, 6, 7, 8, 9, 10, 11. I might have missed one here and I might have missed one here, but I don't think I did because I tried to do it evenly spaced. But we definitely had 1, 2, 3, 4, 5, 6, 7, 8, 9, possibly 10 or 11 periods. So the first one was at if I can get it to come up. Is it going to come up? Very, very small. Okay, at 3:26, and the last one was at 4:28. So basically an hour of sonication. And after an hour of sonication, I stopped recording because I was so excited, as you probably recall from the video, because I started to see a little hydrogen coming in here. There was one blip over here that I missed, this little blip there. But as we came over here, the hydrogen started coming in. And once it started coming in, it started going very, very, very quickly. Now, we did have a container that was full of air, right? The bag was full of air. And inside and above the polycarbonate sheet, there was air. And so it would have to have displaced all of that air and then pushed it around. But the hydrogen then would have come up to the top. So partly what you're seeing here maybe is it building up enough so it bled out of the top of the ultrasonic container. But it does appear to be accelerating, and then it kind of gets to a maximum level up here. Okay? So essentially what you can do... Sorry, I'm not showing you, am I? It starts very slowly, like there's nothing for this period. But I think the first blip of hydrogen here comes about 40 minutes after, no, 26. Yeah, about 40 minutes afterwards. Okay, somewhere around here, about 40 minutes, and then there's nothing really, and then it starts to go bonkers here. Now, what I'm saying is that we are seeing magnesium produced. Magnesium produced magnesium hydroxide. That might be a promoter of the process. Clearly, we can see aluminium oxide in there in these little structures. That would be a promoter of the process. Later, we see sodium and chlorine and so forth. So all of these different things could promote it. So it would accelerate up to a point, and then it might just be, the interesting thing is it completely levels off here. And this might just be because it gets to the point of the maximum amount of hydrogen that can be in the top whilst other gases are being formed. Okay. So what we notice is no mass 2, no mass 19, no mass 20, no mass 35 through to 38, 41, 43. Okay. But over here, we get 41. Well, let's check. Yeah, we got the 41 there. What is the 41 there? Okay. There is some 36 occasionally here, but it's fairly consistent over here. But we also get this 19 and 20 here, and obviously the hydrogen. The 29 seems to go up a lot. The 30 goes up a lot. 31 goes down. 32 basically stays steady. 33 goes up a lot. And 34 basically stays the same. So a lot can be learned from this, and this is where you can come in. But what I want to show you is I did a quick test at the end before I opened the case out, and that was to see what would happen when we did a sample that didn't just look at integer mass numbers. So what the software is doing is it's actually looking at all of the different masses coming in, and it's then fixing them into these particular mass numbers. And because this is a logarithmic scale, look at this 28 figure here. It's 257 at this point. Over here it's 246, okay? But down here, this is 0.76. So whilst this looks like it's maybe 40% of the height of this is 246, and this is 0.76. So this is like 350 times bigger than this bar, okay? This is not very big compared to this. So don't think that this is 40% of this in terms of the number of counts at mass 27. And why that is important, you're going to see this in a minute. Because under here, I have the same chart here, okay? But I'm looking at all of the masses that are coming in with a sort of 0.25 of a mass accuracy, yeah? So a much more accurate type of representation, yeah? And I will actually bring up the trend graph for this as well. There's no trend for this, is there? Analog. Okay, no, there is no. Is there? No, there's no trend. Anyway, so you can see here. Oh, sorry for that. Sometimes you might see, if I change this, you would actually see a little bit of 3. This is going. It's starting a little bit down by 1, but it's extremely low levels. At mass 1.13, it's 0.07, whereas at mass 2 here, which is the peak, it's 4.47. And what you see is this curve coming in. Look at this 27 here. There is a curve that comes up, but it doesn't go down. Look at this mass 31 here. There's a curve that comes up, but it doesn't go down. What am I looking at there? Well, I think what it is that this 27 isn't actually a real 27. I think if there is any 27, most of this 27 here is actually mass 28, because 28 is nitrogen, N2. Okay? N2. And it's such a massive amount, okay, that its trailing edge here is being picked up as 350 or 400 times less, but it looks like a bar here. But it's basically not there. Okay? When a thing is there, like mass 29, it has a curve coming up to it. And it has this comes down and it comes up, right? This comes down and it comes up. That's 30 as real. Don't think the 31 is real. Why is the 31 not real? Well, look at 32 here. This is 46.46. This is just 0.15. 46.46, so this is what, 300 times more than that? 300 times more than that. This is 1/3 of 1% of that, okay? So what is going on? I think this is the trailing edge for O2. This is O2. Oxygen, 216 oxygens. Yeah, they make 32. This is the trailing edge. Yes, there could be sulfur in there, and this is where the problem is with mass spectrometry. We don't know whether this is oxygen or sulfur. Okay? So I don't think we have much 27, and I don't think we have much 31. I think they are trailing. Just like you see here on the hydrogen. Okay? You don't ever have a trailing on the mass one below, right? It's just not there. Why? Because there isn't a mass, one below. But you do have it from 2 to go below. Yeah? So, Gordon, it's great. Yeah, okay. I will see you. Good night. You will be able to have access to this data. And if you have access to a PC or a Mac with Parallels, you will be able to review this data. Okay? Great to have you here. Good night, Gordon. Right, so the interesting thing is 41 and 42. How can we determine what these are? Well, let me try and do that for you. And this is where your homework comes in, when I give you the relevant files to look at. So first off, we have a document that will be in the install pack for the software. So mass number 1, you can see here, you've got hydrogen, but whatever. Mass number 2, hydrogen. You can have various fractions. You see water here, different fractions here. Okay. All of these different chemical compounds, okay, can be those different mass numbers. But it might be a bit difficult for you to correlate this one to this. Okay? So there is also natural isotopes here, which you will also have a copy of. So hydrogen here is 1. And so our first one here, 14. What is 14? Well, 14 is... sorry, that's not mass number. 14 here. 14 there. Nitrogen, of course. Atomic nitrogen. 15. Now look at the atomic... The mass here. This is 0.03. and this one is 4.25. Okay, so it's a very small fraction of nitrogen is nitrogen 15. Oxygen, fluorine here. Fluorine is something that can be 19. Now, it does appear that we observed fluorine. Fluorine is gas. Okay? We seem to have some indication of having fluorine there. Okay? So, correlating these, it's a little bit of a read across, but there is another way that you can do it. Other than the element isotopes, there is another way that you can do this. And I found this rather nice little application which you can use. Rather, it's an online thing. So give me a sec here. And I actually did quite a lot of work for you, and I will probably put this in the blog so that you don't have to do it. Okay. Give me a second. Give me a second. I want more options, and I want molecular weight. Okay, so this is on NIST's website. Okay. And so if we wanted to find something, for instance, at 19, we type in 19 here. And we go to gas phase. I'm going to make this a bit bigger for you. Okay. And we go to mass spectrum. Okay. And then we go search, and it finds fluorine, 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 water made with deuterium, hydronium cation. What's that? That is H3O plus. So that is something that it could be. 19 could be H3O plus. Okay. And it has this nice little diagram of what it is chemically. Yeah. And then the last one is H2O anion. Very similar. This is H3O plus, but this is the anion. Okay. So this 19 could actually be that. What could the 20 be? 20. Gas phase, mass spectrum, search. So you've got neon cation, neon hydrogen fluoride. Ah, well, we've already think we found fluorine, and we already have hydrogen. So maybe the 20 is hydrogen fluoride. Not sure I want to be breathing a lot of that in. Okay. Deuterium oxide, heavy water. Don't think it's that. I don't think it is that, because we don't see a lot of deuterium here. Well, okay. So it is going a little bit towards 3, but not really significant here. Okay, so I don't think it's that. Ammonia. It could be ammonia. Oh, no, it's ammonia D3N. So it's not ammonia there. So, really, is it going to be neon? If it's neon, then we could do a flame test. But if it's not neon, it could be hydrogen fluoride, this 20. We did see, apparently, some fluorine made. And effectively, to create fluorine, you take oxygen and, you know, oxygen 18, which is a real isotope. And if you keep, you know, doing the nuclear process, you end up by producing oxygen and more oxygen 18. And then if you add another proton to it, you know, well, yeah, it got fluorine, 19. Okay? So it could be, the 19 could be fluorine, and the 20 could be hydrogen fluoride. I think that's probably the most likely. So we have potentially fluorine here, potentially hydrogen fluoride here. Okay? Then what do we have? 27 I don't think is anything. And look, let's see what 27 could be if it was a real thing. Gas phase, mass spectrometry, search. Okay. Aluminium ion. Well, of course, it could be. I mean, if you have aluminium hydroxide and you've got some entrained particles, maybe. But is that really a gas phase? Maybe. Aluminium ion. So how do we get the aluminium in there? There's plenty of aluminium in the tank. The point is it doesn't really change throughout the experiment. Look, the aluminium, so we've got up to stable here. So something stable here. Then we start running the reactor, and it really doesn't change much. It just doesn't change much. Okay, so I don't think the 27 is anything. Likewise, where's it gone? What do we think we've got? I mean, hydrogen cyanide? I really hope it isn't. CHN. We know we're making carbon. Okay, so let's try 31, because I think 31 is just this trailing edge here. Gas phase, mass spectrometry, search. Well, phosphorus. We did have phosphorus made, it would appear. Methylidine. Carbon fluoride. Well, maybe, because we've had carbon and fluorine made in there. Nitrosyl hydride. HNO. Maybe. Maybe they're all there. HNO radical ion. It's all there. ALH4 anion. Possibly. Methylamine. Well, we're starting to produce hydrocarbons now. Well, it's an amine because it's got an N in it, but yeah. Okay, so you get the general idea. I think because 31, if we go back earlier in the experiment here, this is about where we're stable, and where we're stable we've got 0.23 compared to 44, and we come over here and well, we got 0.24. I don't think this is anything other than O2, really. So this is where you've got to kind of disambiguate. Now 40 is probably argon. Okay, and this is again very small trailing edge from argon. Look at the scale of argon here. It is 3.16, and this is 0.017, right? So that's 200 times less, whatever. It's not, I don't think so. And basically we'll put in 40, gas phase, mass spectrometry. I think you're going to find that that is argon. Argon, there you go. Argon, argon. Okay? Now, the interesting thing is this 41. Here we don't see any 41. No 41. No 41. No 41. No 41. No 41. And then we start to get 41. When the hydrogen comes up, we start to get 41. What is the 41 here? This is interesting. What is the 41? Okay? 41. What is 41? Can anyone guess? Well, aluminium nitride, ALN, possibly, but that's like a really solid thing. Acetonitrile, CH3N, methyl isocyanide. Lovely. Hopefully not. Magnesium hydroxide cation. Well, we definitely got magnesium. We've definitely got hydrogen, and we've definitely got oxygen. We definitely saw the magnesium synthesized. So maybe this 41 is a magnesium hydroxide cation. We see it appearing only when the hydrogen starts appearing. Okay? It's not down this end. So for me, I think some of the most interesting pieces of data that we're seeing here when we are running the experiment is the emergence of, obviously, the hydrogen, the mass number 19, what is that? Mass number 20, what is that? And mass number 41, what is that? Okay? The last one is 44. What is 44? Can anyone tell me what 44 is? You should know. 44 is of course, carbon dioxide. There you go. CO2. So this is one to watch out for, guys, when we share the data from the thunderstorm generator. CO2, mass 44. Okay? Mass 28 is the mass of carbon monoxide. Because nitrogen is such a huge amount in the gas constituents in air, and because CO is such a small proportion, I don't think you're going to see much of a change there. But we want to look to see if we see a change here when we look at the thunderstorm generator experiment. So I think we have a number of data points that point to hydrogen production, potentially fluorine production, and potentially magnesium production. The silicon might not go anywhere. If you do look at some of these other materials here, and I can bring this up here, I've done the maths for you already, and I'll put this in there. There are things that include silicon in there, in some of the heavier materials, like mass 28 could be silicon. But then there are things like silidine cation. So if I go copy here, and I go new tab, silidine is SiH plus. Silidine, that's mass 29. Does 29 change much? Does 29 change much? If we go over here, I go over there. So we got stable here. 29 is at 1.77. During the experiment, it goes to, wow, it goes to, it nearly doubles, 3.26. Right, so silicon with hydrogen, silidine, and magnesium with hydrogen, 41, mass 29, silidine. So are you getting a thing that we may be producing silicon and magnesium? The magnesium will be assisting in accelerating the process, and the silicon and magnesium produce extra energy. These are the things that will be interesting to find out. So knock yourselves out. I will share all of these links tomorrow. I'm going to go to bed. But essentially, I think what we've been able to show is that aluminium absolutely with... Oh, I've got one more paper to share you. let me share you this. So a couple of years ago, I looked at ultrasonics with aluminium and didn't find anything. But I looked after we did the experiment. In fact, after I got back to the Czech Republic, to see if there were any examples of people using, and there probably are lots, but you know, I did a basic search, and guess what I came up with. This is funny. I found this article. Hydrogen production using aluminium water reaction and electrolysis with ultrasonic wave. Right? Now, we're not doing electrolysis. Okay? But they're adding ultrasonic wave agitation. And this is Didi Risanti, M. Taufikum, N. Fadhila, and D. Arifianto. And this paper was published in the 4th Engineering Physics International Conference in 2023. And I think it came from, I think it was published in December 2023, so December last year. Okay? And so they, again, added sodium hydroxide here into their experiment. And they also looked at that. They used aluminium scrap, which had various elements in it. Okay, no magnesium, no silicon in their aluminium scrap. No magnesium, no silicon. But they do various charts here, and they do various you know, how do we put this? Molar concentrations of the sodium hydroxide. But we have no sodium hydroxide in our experiment. We have no electrolysis. It's just raw aluminium, kitchen foil, and deionized, or sorry, distilled water. Anyway, you can go and have a look at this. It's interesting. And that's about that, really. So, in summary, I think we have found already, with a first look at the aluminium foil, that it gets coated in aluminium oxide. We have seen that the process produces an alkaline solution. Is that only because of the hydroxide ions, or is that because we've got other things like magnesium and potassium and sodium in there also making an alkaline solution? I think it possibly is. Then we are seeing structures where we have a carbon-like biscuit with hundreds and thousands of aluminium oxide on top, with a mixture of elements in there. There's one magnetic particle that we looked at initially, which seems to have a range of different elements in there, but almost exclusively is, well, a vast proportion of it is carbon. Carbon being produced in these systems. And then we found our spot. And our spot is really rather a special thing for me. And I think we're going to find a lot more of those kind of structures when we get some more time analyzing the sample. So maybe I can get that up quickly when I'm not showing that full screen, maybe. Yeah. So yeah, for me, these kind of things were the money shots of the day. So our material here, our magnetic extracted particle, lots and lots of carbon, when the original material had basically none. I think this is a carbon blip down here, but basically it's not going to be more than 4%. These are our hundreds of thousands on our carbon base, on our carbon biscuit, like this biscuit here. What is that? We saw torus-like structures, similar sort of scales to those forming in Benjamin Huang's reactor. These are these fuzzy little things. And then this beautiful spot here. First in our map. Like so. With our substructures here, and then with our line. And what do we see? We saw on here that the silicon and magnesium go up on this ring, and we've got magnesium and silicon here in these ring structures. Okay, so I think it is producing magnesium and silicon. We saw the same things occurring in the Hutchison sample. Magnesium and silicon appear to be produced, so, you know, is it just because we have a cavitation beam coming in here? I'm not sure it is. I think something more interesting is going on. So if you've got any questions, I'll take them now. Finally got through that, so it wasn't so bad. Maybe for you it's a bit technical today. So Bob, where are you testing the generators? Next week, maybe soon next week, I will share the data that we got in California. And again, it will be the raw data and a whole bunch of videos as well. So, I'm trying to get the right mouse here. Okay. So look out for that. You can tool yourself up from tomorrow with the application and the data so you can understand how it works, and also with the NIST database to work out what particular mass numbers correspond to what kind of things. Thanks, Misunderstood. Good night. Yeah, Adonius says this has the potential to really kick off LENR research for the masses if we could. Well, I think really this experiment is so ridiculously simple, and it keeps on delivering. And, you know, it has a lot of logical reasons why it should work. And it certainly appears to do the job. Like I say, I'd love to do this with copper. Do the same experiment, exactly the same experiment. See if you get the same yield of hydrogen. I suspect it would not be anywhere near. The good thing about aluminium and copper, they both don't like storing hydrogen. Aluminium stores oxygen, but neither of them actually like storing hydrogen. So when you have a lot of hydrogen in one place, it kind of builds up. And this is kind of why, if you actually look at Matsumoto's book, he says he chose copper because it's highly conductive and it makes a good cathode. And so being a cathode, it will attract protons towards it and they bunch. And so that's what you need. You need the bunching of the protons and then the sea of electrons that's on the copper surface, because it's conductive, to initiate the formation of what he called itonic clusters. But he says they're the same thing as ball lightning. Yeah, sorry, Laura, distilled water was used, yes. Yeah, Adonis, yes, it would be good to ask them to try it with just water, preferably distilled and deionized water. Yeah, what I'd like to see is, I'd really like to see if we could have a long enough experiment to see if we can actually stimulate an ultrasonic tank to produce the same structures we see, those beautiful apple-shaped structures tearing up the copper that we see in Binger and Huang's experiment. I have a gut feeling we will. And the reason is when you look at the videos that I will share of the capture session on the aluminium foil, you will see that within that hour of sonication, we're already starting to see clusters that look a bit apple shape, have fairly similar collections of these, and they are the right nearly the 20 microns across. So I want to thank again Craig and Benefice Science and above all things and Vanilla Isis for their contributions today. It really helps out. Thank you very much. Yeah. So Adonius says the Quantum Heat site's Ultra document recommends the Vivriel cleaner. It's no longer available. I think, well, anything 43 kilohertz or something would be fine. It actually doesn't matter the frequency, particularly. But since we've done this 43 kilohertz unit, I would suggest trying to get one that has that kind of frequency. Then it doesn't really matter, I don't think. Your standing waves are always going to appear somewhere. There's going to be optimal conditions for a particular device, but I still think you'll be able to do the same kind of thing. So, Vanillice says, Bob, during your work, I see wisps of each part of these Evos, a teasing ghost of the caduceus. Ideas how to see the entire naked form, like when we're able to see the vortexes inside the tornado. I think with better imaging, better time and spatial resolution, and full frame non-scanning technology, so you're not got a frame scan. I'd love to get the new Sony camera, which is just full frame, bang, it does an image. That might not be the best tool anyway. So I think in the UK we're going to do some experiments later in the year where we hire a high frame rate, full image capture. By that I mean it's not like a scanning. ZPE TV says, have you attempted to collect any, I'm missing the bottom there, why is that not showing me, any gases coming off the ultrasonic cleaner? Yeah, that's exactly what this experiment was. That's exactly what you're seeing. Do you mean collect for posterity? No, that was the intention, but what was happening here is you are collecting the gases. So but it's called a residual gas analyzer, and it has a quadrupole mesh spectrometer, something that was invented by, drumroll, Ken Shoulders. Yeah, and I think the interesting bit here is we seem to be creating this 41 signal here. And the 19 and 20 signal, and of course the 1 signal. And I do think we're getting a bit more other ones which we can tease out. Adonius, the brand was important to reproduce the experiment any sonicator should do. Given, yeah. I mean, you can actually buy the transducers, the 43 kilohertz transducers, quite easily, but buying the driver and a container and the transducer, it's just cheaper to buy one of these ultrasonic cleaners. Honestly, though, almost anything should work, to be honest. All that will happen is if you have a different frequency, the size of the magnetohydrodynamic structure will move a little bit wider or narrower. Yeah, well, we've already got pretty good frame rate, and we've also got something that's approaching high frame rate, because I've still framed with a very, very short shutter time on the alpha. However, the alpha does have a scanning sensor, so it's not perfect, but it's pretty good. What I'd really like to do is get like one of these, or a selection of the little yin yangs, but so that we have, I don't know, a ridiculous number, so we can actually see the action of it. Okay, yeah, I know this was a pretty technical one, but for me, it was very important to take you through this tool here, which I will obviously give you access to the software tomorrow, and you'll be able to install it so you are ready to analyze not just this, but the data that comes from the control run, which you've already seen, of the thunderstorm generator and the tests. I think it's going to be very valuable that there are scores of people out there that are tooled up and ready to pass their BDI over the data in the spirit of openness. Just down here, if you actually tail this off, you'll see when the experiment ends here that it just disappears. Like I open it up and boom, the hydrogen just goes doink, 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 doink. And also you can see the 41 here, the 41, 41, 41, and when the hydrogen goes, boom, 41's gone. Look at the 33. Look at the 33. 33, 33, 33, 33. Boom. Drops down immediately. And so does that 29. Okay. I thought the results you were showing was from the material tinfoil. No, that was when I'm showing you the SEM. This is from the SEM. Okay? But what I showed you is there's two potential gaseous molecules that have like, what was it we said? It's magnesium plus hydrogen and silicon plus hydrogen. So the silicon plus hydrogen is the 29, and the magnesium plus hydrogen is whatever it was. I can't remember which ones. So there was two particular chemicals. Where is it? Silidine cation is 20.98. And we went to do, where is it? I mean, you got potassium here as well. We saw potassium form, but it doesn't change that much. Yeah, so we have ZPE-TV. Detection of things that could be due to synthesis. We have apparent synthesis on the foil, which are predicted by the equation, our reaction calculator, wherever that went. I don't know. There we go. So our reaction calculator predicted that the most likely pure aluminium interaction produces magnesium and silicon. Then we see that we produce magnesium and silicon around here, and we see that on the line mark where it's basically in the noise, and then it goes up and it goes up in this spot. And then we see stuff in the data here that support the idea that magnesium and silicon have been made into ions that can be entrained and detected in the detector. I'm sorry if it sounds like Anthony Williams has had an accident, or something. I don't quite know what's going on there, but I'm sorry if that you're alive. That's good. Good to have you here. Philip Mulholland. Bob, I would like to suggest that any molecular species are biatomic rather than multi-atomic. Okay, well, like I say, you're going to have the data. You're going to have all the data. You're going to have the SEMs. You're going to have the time spectra, the end mass spectra, both when the thing is producing gases or still got the gases in play, and then when it's switched off, so you can have the direct comparison of how one collapses away from the other. Okay. And then you are, yeah, so you have everything. It's all going to be raw data. So you can knock yourself out. Yeah, I have to say, again, a special thank you to my good friend and co-director of the MFMP, Alan Goldwater. I'd also like to thank Brilliant Energy, who have loaned us the mass spectrometer for us to use in experiments. And this was the experiment that I wanted to do for years, and it fortunately allowed me to learn the software and get it all running and test it all before we were able to run it with the thunderstorm generator. So everything worked out really rather peachy. But we have a whole series of data here that supports the hypothesis, and I'd like to repeat this with a load of copper foil at the nearest opportunity. And when I do that, I would like to also have a lot longer with the aluminium foil to see what else we can see on those samples. Hi, Malcolm. Yes. Oh, and just lastly, don't forget to get your tickets to either the virtual pass or, and I think if you go to the classroom day, you might even be able to get I don't know whether you can get a virtual pass to the classroom day, but you can get virtual passes to the main days, and they're quite cheap, and I think I gave you even a discount code to those. So, but look forward to seeing you all in North Carolina or virtually online. Thank you, Laura. That's very kind of you to say. It's an ongoing experiment, the Ultra experiment, but yeah. So yes, bit.ly/Cosmic Summit. Okay, if there are no more questions, I think I'm going to call it a night so that I can get all of this material for you tomorrow, so that you can review it at your leisure and come back with what you think each of these mass numbers represent at the various times in the experiment that they are there to do. I mean, it would be nice if someone can look at, I will supply these in the original format and also as a text file. And if someone can pass the data and do, let's say, an average from the time that they, let's say, when the time that the hydrogen starts to appear, like here, where it's fairly consistent over here, if you can do an average over a chunk of that to find out the average kind of mass number concentration, and then an average, sort of here where, it's stable, the opposite end of it, then we can make a real judgment about what is being synthesized and does that correlate with the SEM data that was found. So with that, I will say thank you very much. This was it was, if I can show it, Ultra Hydrogen. This 19th of May 2024. Buenas noches, dobranoc. Good night.